Hey class, it's Mr. Hofstad here with lesson 2 of our 6th and final unit, nuclear theory. Today we're talking about decay reactions. We're going to start off with a bunch of kind of theory and vocabulary and notes, and then there'll be a separate video for the examples. But let's get to it. That's a 30-minute example video, so I want to keep this brief but still clear for you. So we're going to start by looking at the types of different radiation, because all of these decay reactions are going to result in some form of radiation, some energy or particles being emitted during this decay reaction. So what's happening for decay reactions is we have these unstable nuclei. That's kind of a necessity for us to have decay reaction. They are radioactive by definition, and that means they're going to emit different types of radiation. So we've got 3 types of radiation we're focusing on. One type is the emission of alpha particles, alpha particle radiation. Alpha particles are given in our formula sheet, right? They resemble helium-4 nuclei. They are also the least dangerous form of radiation. Low penetration ability. They're not going to pierce much more than the air, because they can be blocked by the skin, they can be blocked by a piece of paper, and even a little bit of air. So the only problem with alpha particles in terms of safety is ingestion of them. So since they do have this +2 charge associated with them, right, when they're swallowed, have the potential to ionize the cells of the digestive tract, right? If we have taken any chemistry, we know that this positive charge can affect and change the charge of the cells that it comes into contact with, right? Even from our electrostatics unit, it can kind of induce a charge in the adjacent cells, and that can be problematic when it starts to change the nature of the cells and cause cancer. Right, so as long as we're not swallowing alpha particles, they're not going to do much harm to us. So that's our first type of radiation. Next we have beta particles, which quite simply are electrons that are at a high energy level. Right, they are excited, they have a lot of energy, they're going to be shot out with a little bit more velocity than an alpha particle would, and they, by effect of that, have more penetration ability. So they can actually go through the skin, so this can become a danger. But if you pile up sheets of paper or wood or even a few millimeters of aluminum, or just stay a good distance away, several meters of air will also block these particles. So not crazy penetration ability, but they still are dangerous to our skin cells, just like UV, ultraviolet radiation. So it isn't ultraviolet radiation, but it'll have the same effect, right? We can have these beta particles, these high energy electrons, piercing our skin and causing some cancer to those outer cells if there is a long enough exposure and they're altering our DNA of those cells. It's also dangerous when we swallow it, because it does have, again, this charge to it, but not as dangerous as alpha particles. Less frequent ionization, right? We only have a -1 rather than a +2. So lower charge, lower potential to ionize those digestive tract cells. Our third and final and scariest form of radiation is gamma radiation. Maybe we've all heard of this. This is the Hulk radiation. This is what Bruce Banner was exposed to. That turned him into Hulk, essentially. But it actually won't do that to you. It'll just kill you. If you want some good visualizations of the danger of gamma radiation, definitely check out the HBO series Chernobyl. I watched that somewhat recently, and it really puts into perspective how dangerous this is and how we really need to work to control anything that has the potential to emit gamma radiation. All right, watch Chernobyl. You won't regret it. Well, you might, but it'll be eye-opening. So gamma radiation is high energy photons, so not electrons. We're working with photons here, so not the mass or anything like that, but they are extremely high frequency, right? If we look at our electromagnetic radiation spectrum, gamma radiation is the farthest to the right of that spectrum, which means it has the highest frequency, smallest wavelength, also the highest energy. So with that energy, we get this potential for extreme penetration. They can pass right through the body, right? It's like shooting tiny bullets right through your body. The only real guard we have is several centimeters of lead, a couple meters of concrete, or several kilometers of air. That's a scary thought, that these gamma radiation, high frequency photons can travel through kilometers of air and still pass right through you. So since it can penetrate through the entire human body, they can ionize any cells, right? Even inside the bones. They tend to pass through the body without ionizing any cells, so they're only dangerous at high intensities for long periods of time. So even though they can pass through and they are like being shot with tiny photons, unless you have a long exposure, chances are they won't ionize enough of your cells to cause permanent damage, right? So you do have to be very worried about this, but most likely in your lifetime you'll never become exposed to that high enough intensity for a long enough period of time, right? That intensity for that period of time would be like the first responders, the firemen, or the plant workers at the Chernobyl site, because that was an extreme high intensity. All right, we have these three types of radiation. We can separate them using magnets or electric fields, right? We have our magnetic field here with our fletching of our arrow going into the page, right? X means in, circle means out. So if we are emitting this radiation through our magnetic field, right, we know that we're going to cause this uniform circular motion, right? Especially with our negatively and positively charged. Remembering back to our magnetism unit. And we have an electric field, right? Again, our charged particles will be attracted or repelled from plates, right? Alpha particle would be attracted to the negative, beta would be to the positive. So we have to take note that we are constantly being bombarded by low amounts of background radiation, right? This comes from the sun, from radioactive material stored in building materials like bricks. These are very low doses, of course. Radioactive material underground, right? This stuff is everywhere. It's very natural, but it's all low intensity exposure. So the cells are able to be repaired as long as there's not a high enough intensity or a long enough exposure to a high intensity. So the only time we have to be worried about radiation is when we're exposed to a huge short-term dose of radiation. So that's going to be a high intensity. So that would be, I don't know, an X-ray would be kind of an example of that, but even higher intensities than that, like a nuclear reactor exploding. So that high dosage can result in radiation sickness and often death. Another problem is when you're exposed to a moderate, steady dose of radiation, which often leads to cancer. I've heard that pilots and people who are flying often have this moderate, steady dose, which can be problematic. But not an expert on that. So if you're planning on being a pilot, don't be afraid. All right, those are the types of radiation. Let's look at where that those radiated particles are really coming from. So we've got 3 types of, or actually more, 4 I think, types of decay reactions we're going to look at. When we're balancing our nuclear equations, we get to keep in mind that the top numbers, right, the number of nucleons, protons plus neutrons, needs to obey the law of conservation of nucleons, which is our, if we look on our formula sheet, our 8th principle of physics. So the total number of nucleons needs to be conserved whenever we're going and balancing a decay reaction. And likewise, the bottom number, which is our protons number, right, must obey the law of conservation of charge, principle of physics 7. So we need to maintain the same number, the same amount of charge throughout, and the same amount of nucleons whenever we're undergoing a decay reaction. All right, let's try out this example. We got, well, first of all, when a nucleus has too many protons, this is what's going to cause our alpha decay effect. So too many protons is going to result in alpha decay because the electric force of repulsion is too high, right? We have an electric force of repulsion between these protons, and it's going to be too high for the nucleus to be stable, right? It's going to be greater than our strong nuclear force, right? A strong nuclear force won't be enough to keep holding these protons together for much longer. So instead, right, we're getting the nucleus shooting off this alpha particle. It's going to reduce not only, so alpha radiation, obviously, we're emitting an alpha particle, alpha decay, alpha particle should be pretty obvious there. It's going to reduce the size and charge of the nucleus, right? So not only are we getting less overall nucleons, we're also getting less charge on that nucleus of our element. So since the number of protons changes, the elements change, which we call transmutation, right? We've transmuted, we've essentially transformed into a different element. So let's try this example. We've got radon 222. So we're going to write it in our nice standard atomic form. We got the number of total nucleons at 222. That is our mass number. And if we look at our, what's it called? Wow, table of elements. That was too hard. We've got 86 protons. So our atomic number is 86. And we know we're going to undergo alpha decay. So we're going to need to emit an alpha particle, which is like our helium-4. So we have 4 total nucleons, 2 protons, and this guy would have a charge of 2+, right? Because we have 2 protons. And, right, we need to discover what our daughter nucleus would be. So this would be our parent, and we're looking for what our daughter. So we're going to look at our top numbers. I'll keep these in 2 different colors actually. So the top numbers, those ones are going to obey the conservation of nucleons. That is our principle of physics number 8. conservation of nucleons. So that means the total number of nucleons remains 222. Okay, so we have 222 on this side. We need to have 222 on this side. So we know we have 4 nucleons from our alpha particle, and we're going to need to have 218 from our daughter nucleus here. So, right, 4 plus 218 is equal to 222. All right, that's our conservation of nucleons. Then with the bottom number, we are going to look at principle of physics 7. We need to have conservation of charge. So that means the total charge needs to remain at positive 86. We need to have 86 protons. So we got 86 on our left-hand side. We got 2 there. So we're going to need to have 84, because 84 plus 2 is equal to 86. All right, so we'll use that number of protons to determine our element. We've got polonium, 218. All right, now the question also wants us to look at conservation of momentum. So here we need to have, well, actually they're not telling us anything. This will be used for later on questions. But for our momentum to be conserved, back to unit 1, very distant, very long ago, I know. We have the momentum total at the start needs to be equal to the momentum at the end, which we use our little single quotation for, our prime. So after the impact, or after the collision, the emission, we need to have the same overall momentum. Another way we can write it is if our parent nucleus is at rest, we have a 0 momentum. That means that the momentum of our alpha particle plus the momentum of our polonium in this case, or whatever our daughter particle is, plus if we have any gamma radiation, that momentum of our gamma photon would also need to be taken into account. So you won't always have a gamma, right? We'll look at that in a second, but if there is any gamma radiation present, you need to take that into account in your momentum conservation. All right, finally, our conservation of mass energy. We need our total energy, our total mass energy at the start to be equal to the total mass energy at the end, our prime situation. So total energy at the start is going to come from always our mass defect. Because we don't have any other way to have energy from this parent nucleus at rest. So the mass defect energy will be equal to the kinetic energy of our alpha particle and the kinetic energy of our daughter, which in this case was polonium. And if we have gamma, we'll have the kinetic energy of that as well. So all the kinetic energy is coming from our decay side, whereas the energy initially is coming from the mass defect of our parent nucleus. All right, let's keep going on with the notes. This example you can find in the attached video from Mr. Holloway. Longish example. I believe in you though. All right, here we have beta decay. So there's two types of beta decay. We have beta negative decay and beta positive decay. It depends on if we're emitting this high energy electron, this beta particle, and an antineutrino, or if we're emitting a positron, right? Positron would be positive, this electron would be negative. So nice and easy naming, should be good to keep track of that. So beta decay, either one of them is going to happen when we have too many neutrons. So instead of having too many protons like we did with our alpha decay, we now have too many neutrons to be stable. Due to the weak nuclear force, this is a bit of an extension past the Alberta curriculum. You just need to know that this is what causes neutrons to change into protons. So weak nuclear force will always be responsible for changing neutrons into protons. And if you are curious about weak nuclear force, as it is one of our 4 fundamental forces, I've attached some nice videos from our favorite crash course guy on weak nuclear force as well as strong nuclear force. That's kind of extra learning. Don't watch that if you're feeling overwhelmed by any of this, just if you want to extend your understanding a bit. But as far as the Alberta curriculum works, we only need to know that weak nuclear force changes neutrons into protons, right? Don't have to get too hung up on the up quarks and down quarks, but it's interesting stuff, so check it out if you want. So we're getting a neutron changing into a proton, and since we need conservation of charge, we need to balance that out by emitting an electron. Since we're going from neutral to positive, we need to also have this negative high energy electron and this antineutrino, which we draw in as this. So all the energy released is due to mass defect in our parent, right? Here we have our high energy electron, our daughter nucleus, and this antineutrino. Sometimes you can see we'll get gamma. And we'll get to gamma and what that means in a minute. So this is almost identical, right? Second type of beta decay, but here we're getting a proton turning into a neutron. So since we're going from positive to neutral, proton to neutron, we're kind of losing some positive charge. So in order to respect our principle of physics number 7, our conservation of charge, we need to add a positron, which is an anti-electron. Positron is like an electron, but with a positive 1 charge. So this again is weak nuclear force. Whenever we have protons turning into neutrons or vice versa, that is due to our weak nuclear force and switching up our quarks via our bosons. Check out those videos if you are at all curious what a boson is. So we have a parent, and we're going to emit this positron. Right here we have, instead of the negative 1 proton, we actually do have 1 proton in value, not really in, I guess it kind of is in mass too. So a positron is the antiparticle of an electron. We'll get to more of that later. Our daughter, and again a neutrino. Here we had an antineutrino with the line on top of it, here we have just a neutrino, no line. All right, so neutrino will always be this weird curvy V. Anti will have the line on top, right? And that's going to be associated with our negative emitted electron, whereas a neutron won't have that. All right, now on to our most dangerous form, our gamma decay. So gamma decay actually doesn't have anything changing from protons to neutrons or emitting particles with big masses like alpha particles, but it's actually a result of alpha and beta decay in certain situations. When we undergo these first two types of decay, or three if you're considering positive beta decay to be one on its own, then the nucleus can be left in an excited state. Just like we can have excited electrons, right? Our high energy excited electron. We can also have excited nucleus. So the excited state of the nucleus is unstable. It wants to return to its ground state, just like high energy electrons that have recently absorbed a photon are going to want to return to the ground state, thinking back to our hydrogen electron orbitals from the end of Unit 5. Something similar is happening with the nucleus here. So we want to go from our excited, unstable state to our stable ground state. But we need to do something with that energy, because the excited state has high energy, ground state less energy, but that energy is being converted to this gamma photon, very high energy. So we're emitting this high energy gamma photon. There's no transmutation since we're not altering the number of protons or even neutrons. So our reaction can be written with this. Keep in mind we got this little asterisk here denoting we have an excited nucleus, and we're losing that excited asterisk, right? So really focus in and remember to include your little asterisks. That means excited. Because who isn't excited for little asterisks? Excited. Wow. I'm terrible at writing with my trackpad. And we're also emitting, of course, this high energy gamma ray. So that's why for all of these we had our brackets around the gamma ray. So sometimes we'll get a gamma ray. So here's how we know when we're getting a gamma ray or not in all of our alpha and beta decays. So when a radioisotope goes through alpha decay or beta decay, either or, there's two possibilities. We can have only the alpha particle emitted with very high energy. So we're going to get the alpha particle shot out at a big speed, lots of kinetic energy on that alpha particle. Or we'll have the alpha particle emitted with lower energy, but that daughter nucleus that's left behind is going to be in an excited state. So the energy that wasn't sent off with the alpha particle because it's just slowly drifting away versus being launched out with very high energy, all that extra energy is stored up in the daughter nucleus. It's in this excited state. It has the little asterisk beside it, and it's going to eventually drop down to ground state, which will emit one or more, depending on how much energy we're talking about here, gamma photon. That's it for the notes. The rest of the examples can be found in our next video. This is a longer lesson, but we only got the one this week. I believe in you. Please let me know if you have any questions. This is pretty challenging, pretty high level stuff. So don't feel bad if it takes some time to work through. Good luck. I will see you all next week